Okay, good morning, everybody. It's a pleasure to have here today for the first colloquium of the year, Professor Stan Owocki from the University of Delaware. So just to give you a brief overview of his activity in astrophysics, let me tell you that Professor Owocki started working on the solar wind in Boulder for his PhD, and then moved to, as usual, as postdoc to different places, Harvard and San Diego. And finally, he got his position now at the Bartol Research Institute in Delaware. He's a theoretician of stellar winds. I skipped to say that he first began with the solar wind, but then he, after the PhD, moved to massive star winds, a topic in which he has been working for the last 25 years, 30 years. And on different theoretical aspects of these stellar winds. He has been always a step ahead of the standard knowledge about stellar winds. So he has worked on wind instabilities, wind magnetic fields in the winds well before they were subject of observational interest or observational application. So his talk today will give us an overview of the present status of our knowledge about stellar winds that, as you know, determine, in the case of massive stars, the subsequent evolution of the star, and then it's high interest to all of us that work on this, for me at least, very, very interesting optics. So Stan did a large trip to come here, so thank you very much, Stan, for being here, and please go on.
Okay, so first of all, let me say I'm very, very honored to be invited to come here and more give this first in the year's series of colloquia. I had a chance to look at the schedule of the talks that you're going to hear, and I hope you won't be too disappointed with the mundane topic of near stars when you're going to be talking about sound waves in the early universe the next month. And also when I look at the list of people who have been previous speakers in this series, it's really quite an honor to even be considered in the same breath with some of those people. I also very glad to have an opportunity here to visit for the first time a place that I've heard so much about through my various colleagues and also talking with Artemio. It's a great honor, and I'm looking forward to being able to see the observatories on this weekend. We're going to go up to the observatory here in Tenerife, and then also on La Palma on Sunday. I will be here until next Thursday officially, although I probably won't be around too much after tomorrow because I'll be traveling to La Palma, but I will be around, I think, on Wednesday. And the reason I'm mentioning that is that in case you want to know some more about or want to discuss some more about some of the topics that I'll be covering today, I'll be happy to have a chance to speak with you in private. So basically, as Artemio said, I've been working on massive star mass loss for really 30 years now. I started working in 1982 on this topic. And so it's really quite a accumulation of details, as you will. And sometimes the greatest challenge of a talk like this is to figure out a way to sort of summarize some of the interesting physics without overwhelming people. So let me just start by plugging the idea that massive stars are very important objects, even though they're mere stars. They really are powerhouses of the galaxy and of the and of the universe, and they're cosmic engines, as we call them, and cosmic beacons. And for example, if you look at a galaxy, the spiral arms are dominated by massive star light. Even though massive stars themselves are very rare, they're so powerful, they dominate the energetics of galaxies. For example, in these very dense star-forming regions in spiral arms, which are characterized here by the red H-alpha emission from the H2 nebulae. And they also blow, they're so luminous that they have a huge mass loss driven by the radiation from the star. And so they blow these bubbles into the interstellar medium, and then those bubbles compress the material and then sometimes help trigger new generations of star formation. So you typically see massive stars playing a very dominant role in the energetics of these nebulae. And one of the key places where we can really study massive stars is in the Keyhole Nebula of Carina. And this object right here in particular is quite well known to many people. This is Eta Carina. It's one of the most massive stars in the galaxy. And in this case, the mass loss from this star is just enormous. The solar wind loses about 10 to the minus 14 solar masses per year. Massive stars quite regularly can lose 1 billion times more than that. And in case of Eta Carina, during its 1840s, it had a giant eruption. It lost a solar mass per year, and it created this nebula called the Homunculus Nebula. So mass loss from massive stars can really be incredibly dominant. And we really like to understand what causes it and what its consequences are and what role it plays. So let's just consider the basic physics of what's going on in these massive stars. And really it comes down to two things. Gravity is trying to pull the star together. And gas pressure, of course, normally is support for holding up a star like the sun. But in very massive stars, it's the radiation pressure that's most important. And you can write the radiation acceleration as an integral over the flux times the opacity, the mass absorption coefficient, divided by c. Changing from flux divided by c changes energy flux into momentum flux. And then mass absorption coefficient just tells you how much of that flux gets absorbed per unit gram, which gives you an acceleration. And you have to integrate over the spectrum of the star. The key problem with this now is that normally opacity, where there's a lot of opacity, there's very little flux because photons will get around the places where there's lots of opacity. But if you just have free electrons, for example, which are gray opacity, then you can just pull that out of this integral, and you find that the ratio of the radiative force due to free electrons to gravity is just proportional to this ratio of luminosity to mass. The radius cancels. And we call this the Eddington parameter. And when this parameter gets to be of order unity, then you know the star is in trouble. It basically has radiation pressure that wants to sort of overcome gravity. But the thing is, it doesn't happen for ordinary stars. In the case of the sun, this ratio is only about 10 to the minus 5. So you can pretty much neglect radiation forces in stars like the sun. But stars have the property that their luminosity increases as a high power of the mass, typically 3 or 3.5. And so when you go to stars that are 10 or 50 solar masses, this ratio, even for a free electron, starts to become of order unity. And then if you take into account the fact that there is other kinds of opacity besides free electrons, namely lines, bound opacity, then it starts to become possible for this force to become greater than unity and drive an outflow, which is what we could call stellar wind. Now, the key thing is, first of all, if you're just going to rely on the free electrons to do it, you'd have to get to luminosities of the order of 1 million solar luminosities. But that's exactly what the luminosity of Eta Carina is. It's 5 million suns. And so Eta Carina's eruption was probably triggered by some kind of super Eddington outburst where for a while it actually got brighter than the Eddington limit. But in ordinary massive stars, it's this enhanced opacity due to lines, which is actually driving the mass loss. So here's the basic way you can think about line opacity. Line opacity is like a resonance process. So if you think of, for example, blowing with your lips into open air, you make kind of a broad sound. But if you put it, and you can whistle, and I can't whistle on demand, you make a much louder sound with the same amount of air, but it's attuned to a certain specific frequency. That's basically due to a resonance process inside of your mouth. Well, the same process happens in atoms. And because of this resonant, line opacity is enormous compared to continuum opacity. You take an electron and put it from a free state into a bound state, the opacity goes up by a factor of 10 to the 7, which is the quality of the resonance oscillator. And even when you average over the fact that most of the electrons are only a few of the electrons that are in an atmosphere of a star are in bound states, you still get a force that's greater than 1,000 times that of free electrons. if you could expose all this light. But the problem is that line-opacity tends to self-shadow itself. We know that when we look at a spectrum of a star, there's no light coming out in the middle of the spectral lines. And so the key for making line-opacity work is to de-shadow it by Doppler shifting the absorption of given opacity out of its own shadow. And that requires a velocity gradient and allows you then to sweep through the spectrum. And then the radiation force on optically thick lines requires it to be an acceleration divided by the density. And if you solve this problem, which is what was done in the classic paper in the 1970s, Kastrov and Klein, you can actually derive analytic formulae for how much mass will be driven from the star and what kind of flow speeds it will have. So this is all very well-established theory that goes back more than 35 years now. All right, well, let's just talk about what are some of the consequences of having radiation-driven mass loss. Well, I've already mentioned one, that when you get near the Eddington limit, you can have these giant eruptions like Eta Carina had, and this might actually be playing a key role in setting the upper mass limit for stars. Why are there no stars that are 1,000 solar masses? Why is the upper mass limit of stars that we've ever seen about 200 solar masses? Well, it almost certainly has something to do with the Eddington limit. Now, the details of how that occurs is a real interesting research problem, which I don't have time to discuss today because I can't tell you about 30 years of research in 45 minutes. But anybody who's interested in talking about this problem, I'd be more than happy to discuss it more with you. The second question is that many times massive stars are in binary systems, and you have two massive stars, and then the winds actually smash together and make these big collision shocks, and it produces very, very hard X-rays, several keV X-rays. And we can see those X-rays, and I'm sure some of the people here are interested in X-rays. And again, I've worked a lot on that with my students on colliding stellar winds. The next issue is that sometimes massive stars, the secondary star has exploded as a supernova and left behind a compact companion remnant, either a neutron star or black hole. And now the stellar wind can feed accretion onto the star and drive a powerful jet. And this can lead to really hard X-rays, tens of keV, or even gamma rays. And I know there are some people here that work on these that are related to this TeV telescopes, these Cherenkov telescopes. And I've also worked a lot on that. And so anybody who has interest in that, please let me know, and we can have some interesting discussions. But what I'm going to do today, because I wrote this abstract with a very optimism that I'd be able to cover all kinds of interesting things, I'm going to focus on one specific aspect that's come about in massive stars, namely that a subset of massive stars have very strong magnetic fields. And I want to ask the question, what happens when you have these magnetic fields and you have solar wind mass loss? How do they compete with each other? And it turns out what they can do is they can feed what we call a magnetosphere around the star. So the topic I'm going to talk about, the rest of the talk will be about wind-fed magnetospheres of magnetic massive stars. And these are my collaborators. This was my postdoc, a graduate student, later a postdoc. Another postdoc, Veronique, is somebody who I've pending an SF grant. If it's funded, she'll be coming to work with me as postdoc. Greg Wade runs this thing called the MIMES Consortium for Magnetism and Massive Stars, and there's the logo. You can find it on the web page, on the web. I'll be talking quite a bit about this MIMES project. Okay, so first of all, the word, yes. They're relatively rare, a few percent. It depends on the spectral type. Okay. But it's also not clear whether it's a matter of detection limit, how if you went down a low enough limit, how big it. But the ones we're talking about today are only a few percent. They are very, very powerful, over 1,000 Gauss global fields. Now, the concept of a magnetosphere really goes back to the Earth and the Earth's early days of the space age when they first flew satellites around the Earth, and they found there was all this trapped plasma around the Earth. In the case of the magnetosphere of the Earth, this plasma is primarily origin from the solar wind. It comes in here and it leaks through the bow shock, and then eventually gets into this stretched out magnetosphere. So I like to call this like an outside-in compressed magnetosphere. It's being compressed by the solar wind, and it's the fact that the Earth has a magnetic field. But when you have the sun, you can have plasma that's trapped on magnetic loops where the plasma is coming from below. So this is like an inside-out compression, of trapping of plasma. Beautiful picture here from trace of the solar atmosphere. And we know that, going back to the work by Hale, that the sunspots on the sun are actually magnetic, very, very strong, regions of strong magnetic fields, several thousand Gauss, because we can see this Zeeman splitting directly, where the energy levels is split by the magnetic field, and it actually splits into 3 different lines here. And so this is the way we know that magnetic fields exist on the sun, through spectral polarimetry, looking at the fact that the lines are split and they're also polarized. We'll talk about that in a minute. So when you look at the solar corona in the solar atmosphere, in ultraviolet or X-rays, you see this trapped plasma that's very hot, millions of degrees, that's very strongly organized by the magnetic field of the sun. Now, even in white light, you can tell that there's a magnetic field if you take one of these nice pictures that are taken with a radially density filter. This was taken by my former colleague, associate, director of the High Altitude Observatory when I was a graduate student, Gordon Newkirk. And he developed this radial density filter. And it allows you to see a big dynamic range in brightness. You can actually see these structures which are held closed by the magnetic field, but then are pulled open by the expanding solar wind. So, all right, now just to get ourselves oriented, this is the luminosity versus temperature, the so-called HR diagram, and here's the sun, and the stars that we're going to talk about now are way up here, many tens of solar masses, and instead of having coronal hot pressure-driven winds, they have radiation-driven winds. And they also, whereas the sun's magnetic field is driven by a rotation convection dynamo, making an active activity cycle of generating magnetic field every 22 years, or 11 years, and then canceling it and then regenerating it. In the case of high mass stars, the temperature on the surface is so hot that hydrogen hasn't recombined, and therefore there's not these strong convection zones. The envelope is pretty much radiative. And so you don't actually expect magnetic dynamos to occur on massive stars. And so why would they have magnetic fields is really a bit of a puzzle. But they do. To summarize, hot massive stars have strong radially driven solar winds. The mass loss rates can be billions of times that of the solar wind. Some are observed to have very strong large-scale fields, like dipole type of fields, on the order of 1,000 to 10,000 Gauss. They're very stable. They don't change over activity cycles as far as we can tell. They're probably not from a convective dynamo. They're probably fossil fields that were formed in the early phases of the star formation, either from the interstellar medium compressing the field being compressed as it froze into the collapsing cloud, or from some sort of active dynamo that occurred during the early pre-sequence fully convective phase. The other thing about massive stars is they tend to be very rapidly rotating. A couple hundred kilometers a second rotation speed at the equator is not unusual, whereas the sun only rotates at a couple of 1 kilometer a second, 2 kilometers a second. So these stars have very rapid rotating, and indeed, they're half of the rotation speed you would need to go into orbit at the equator. And so the rotation plays a big role in massive stars. And what we're going to basically talk about is the combination of these 3 things: radiation-driven winds, a magnetic field, and rotation. So let's go back to how do you actually infer magnetic fields from massive stars, since you can't actually look at sunspots or any individual features on the surface. And the answer is that not only is this Zeeman splitting the line, it actually, the different components are oppositely polarized, circularly polarized. And so the so-called Stokes V parameter is the difference between the left and right-handed circularly polarized light. And that is directly proportional to the parallel component of the magnetic field. So as you look across the spectrum of a star, if you see this kind of asymmetric Stokes V profile, then that is a direct signature of a globally average longitudinal field along your site. So even though you can't resolve the star, you can actually see that there's a global magnetic field on the star if it's large enough scale. So there's these beautiful instruments that have been put on a few meter class telescopes in Hawaii, in France, and in Australia, which have high resolution power and spectral polarimetry, and they can actually detect these magnetic fields. We now have detections in over 3 dozen OB stars earlier than B2. All right, and so this project, Magnetism as the Stars, was started a few years ago by Greg Wade, an observational project, which then has theorists like myself working together hand in hand with the observers to try to understand the results of the observations. And there's the website for that. So now, what we want to ask as theorists here, how does the magnetic field interact with mass loss? How does the magnetic field channel the wind into a magnetosphere? And what happens to this magnetosphere? It can either be, if the star is rotating, it can be centrifugally supported. If not, it just sort of dynamically suspended and falls back down. And then this magnetic field also can play a role in angular momentum loss through what's called magnetic rotational braking from the star. And this can lead to spin down of the star's rotation. So now, let's go back to the solar corona again and just review this picture. This is now a negative image, where we notice that at some sort of characteristic radius, the field lines go from being closed to being open. Okay, and that's because the outflowing stellar wind actually ends up dominating in the energy and actually pulls the magnetic field lines open. And then there are current sheets along these streamers that account for the fact that there's an opposite magnetic polarity on each side of this streamer. And so we can do the similar kind of modeling for a radiation-driven wind, only now you calculate the radiation force through this CAK theory, and you put it together with the magnetic field, and you want to characterize what will happen depending on how strong the magnetic field is compared to how strong the wind is. So this parameter eta is kind of like an analog to the so-called plasma beta, except that it's the other way around. I put the magnetic field on top. And it's, instead of having gas pressure here, it's the dynamic pressure of the stellar wind that is the key thing. So this is like the kinetic energy of the wind. This is the magnetic energy density of the field. And if you now go into a situation where you ask at what point in the distance expansion will these two parameters be equal, that is it's called Alfvén radius, where the flow speed is equal to the Alfvén speed, or the energy density of these two things, the numerator and the denominator are the same, that will occur at a radius which is set by this parameter, sort of the surface values of the field and the properties of the stellar wind, to the 1/4 power, because the energy density of a dipole field falls off like r to the -3. The square of that falls off like r to the -6. But once the wind gets to its terminal speed, it only falls off like r to the -2. So 6 minus 2 is 4, so the 1/4 power of this parameter is where the wind will win out. And that point we call the Alfvén radius, and you can see that's the point where the magnetic field goes from being closed to being ripped open by the wind. And now if we just run this as a simulation, what we can see is that everywhere below the Alfvén radius, material that is driven up the opposite foot points and collides at the tops of the loops eventually just compresses and cools, and then just falls back down on the star. Whereas material above this Alfvén radius basically gets pulled out in a very dynamically complicated outflow. Now these are just 2D axisymmetric flows with the field with no rotation. And there could be, of course, much more complicated situations occurring in 3D, but this gives you the basic idea that the stellar wind basically, it would normally flow outward, gets trapped by these closed loops, and is forced to fall back down on the star. And this is what we call a dynamical magnetosphere, because material is suspended above the star for a while, but it is always falling, rising and falling. It's kind of like throwing balls up in the air if you're juggling. There's always some balls in the air, but they're always in the process of either rising or falling. Okay? But on average, if you were to take a picture, time-lapse picture of balls being juggled, there would be balls in the air that you couldn't understand if you didn't know the fact that there was a juggler underneath. And so that becomes like what we call a dynamical support for a magnetosphere. And now let's consider what happens when you add rotation. When we add rotation, you now have a new parameter, the rotation speed over the critical rotation speed, which is the speed at which the material would be at orbit. And at some radius, which is given by the minus 2/3 power of this parameter, if the gas is rigidly rotating, then the centrifugal force will balance gravity. And at that point, at this Kepler radius, above this Kepler radius, the material will not be able to fall back down because the centrifugal force will be greater than gravity. So when we turn on the simulation in this case, we see that material below the Kepler radius falls back down, but material between the Kepler radius and the alpha radius gets trapped. It wants to basically be centrifugally driven outward, but the magnetic field is holding it down. And so you get an accumulation of material in between these two radii. And we call that a centrifugally supported magnetosphere. Here's a zoom in on that process. It's between this Kepler radius here and the alpha radius, which is about here. The material is basically trapped. And so it builds up to a very high density, and this is something that we could potentially observe because there's a lot of material now trapped around the star. It's been fed by the wind, it's been held down by the magnetic field and forced to co-rotate with the star, but then it's basically sitting there at temperatures of 20,000 Kelvin. It's going to emit like crazy in lines like Balmer, hydrogen. So let's sort of take a quick step back here to review where we've been. We have two parameters, this magnetic confinement parameter, which determines the alphane radius, and we have a critical rotation parameter, which determines this Kepler radius. And so now if we now make a graph where we put magnetic confinement parameter on one axis and rotation on the other axis, relative to the rotation, then we can define a place, well, below this line, magnetic fields are not very important because they're not able to ever dominate the dynamics, okay? But above this line, magnetic fields can be very important from the dynamics. Above this line, where the Kepler radius is equal to the alpha radius, you can have magnetic fields that are centrifugally supported. Gas that's above the magnetic field that's centrifugally supported. Here, material just falls back down. It's a dynamical situation. So now we can populate this diagram with observed stars, and there's only about a dozen on here, but now we know about 3 dozen in the latest rendition. I'm actually in the process of writing a paper with Veronique where we put the 3 dozen stars on there, and we talk about how their position on this diagram relates to their observational features. Okay, so this is what we can do MHD simulations out to about a magnetic confinement parameter of 1,000. The reason why you can't do any more than that is the magnetic field gets very stiff. And doing numerical simulations of a very stiff magnetic field is very difficult because the alphane speed becomes very, very fast. And then you have to make very, very tiny time steps. But you see, so that means that all these stars up here are not really accessible to MHD simulation. On the other hand, they are so strong, the magnetic field is so strong, the magnetic confinement is so strong, that the entire region near the star is completely dominated by magnetic field. And so we can think of this region as being a region of rigid field hydrodynamics. It doesn't have to even be full MHD. It can just be considered that each magnetic field sort of defines a one-dimensional tube along which material can flow. So here's an example of a simulation in this rigid field hydrodynamic limit. Now what we find is that each magnetic field line simply guides material from the surface onto this magnetically confined disk, if you will, and below the alpha Kepler radius, material falls back on the star. Now, what's neat about this simulation is it's actually 10,000 one-dimensional simulations stitched together. Now, if you know anything about modern computers are very well adapted to problems like that, where you can put 10,000 individual problems on a big cluster, and they just all run in parallel. So this runs very, very fast. And you can do incredibly detailed simulations. For instance, in this case, we're actually seeing the material comes up here and shocks as it hits this wall, and there's a big region of hot emitting gas that's X-ray, that's going to emit X-rays. This is on the order of 10 to the 8 Kelvin. But eventually it cools, and it settles down into this dense disk at the tops of these magnetic loops. So now, think about this whole process then. It's kind of like filling a glass of water. The magnetic field, the radiation driving is driving material up these foot points of these loops. They crash together at the top and they get stuck by the centrifugal force here at the top of the loops. So in some ways, this whole process is like filling a glass of water. When you turn on a glass of water, sorry about that. when you turn on a glass of water, I don't know how to shut that off. And hopefully they'll go away eventually. So when you open a faucet, the filling of the glass is very, very complicated. If you were to study the hydrodynamics of that, you'd really go crazy. But at the end, you know that the material eventually just settles in to the form of the glass, which sort of defines the potential well of the water sitting in the gravitational field. And analogously, if you think about it for a minute, you have a situation where you have gravity and pulling things inward, and you have centrifugal force pulling things outward in a rigid body rotation. Well, that could be written as a scalar potential. And so in this next diagram, in this next diagram, what we're doing is just showing magnetic field lines colored by the potential due to centrifugal force, gravitational force, plus centrifugal force. Near the surface of the star, the potential is very low because gravity is pulling things in. But away from the surface of the star, near the tops of these magnetic loops, there's a centrifugal force that pushes outwards. So the centrifugal potential goes down at the top of the loop. As you follow any given loop, you go from blue to red, back to blue again. Blue to red, back to blue again means low potential, high potential, low potential. And if you can get over this hump in the potential, the material will tend to accumulate at the minimum of the potential, just like water tends to accumulate at the inside of a glass, depending on the shape of the glass. So if we can just define the shape of this potential, we will already know where most of the material is going to end up after being filled with stellar wind. So, of course, for a field-aligned rotation, which is what this is illustrating, the magnetic field dipole is directly along the rotation axis. This minimum potential is just an equatorial disk starting at the Kepler radius and moving outward. You expect material to accumulate on this disk. But the neat thing is that this is such a simple mathematical problem. It can be solved with semi-analytically. I did it first with software called Mathematica. You can define the surface, and now my colleague does this with IDL. You can define the shape of this minimum potential for any arbitrary tilt angle between the magnetic field and the rotation axis. So you're not just restricted to a dipole that's aligned. You could have a dipole that's tilted. And indeed, if you think about it, since it only cares about the magnetic field along, the flow along a given magnetic field line, you could have any arbitrarily complex magnetic field. If you could define the magnetic field at the surface, and then just define its form in the circumstellar environment, you could find the shape of this minimum potential throughout the magnetosphere. And material is predicted by this model to accumulate on these minimum potential surfaces. So this is like almost like an analytic problem. You can actually define these surfaces sort of semi-analytically. So now let's just see what happens in a specific case. This star Sigma Ori E is in the Orion. It's a B2 star, which is known to be strongly magnetic, about 10,000 Gauss magnetic field. Sorry, again. And it has a very huge magnetic confinement parameter, 1,000,000. So the magnetic field is completely dominant, but its angle, its rotation axis and the magnetic axis are tilted by about 55 degrees. So now what we can do is just fill up this surface, this tilted surface, with plasma and put it in hydrostatic equilibrium and let it be in radiative equilibrium with the star. The star is about 20,000 Kelvin, and in radiative equilibrium, the gas around the star will also be around 20,000 Kelvin. So this is an analytic model of a magnetosphere where you just basically populate the material along this minimum potential surface in hydrostatic equilibrium. And then you just look at what it would look like if you were to look at it in, say, a line, a spectral line, where it was emitting like a given frequency. And of course, I'm thinking of, say, for example, H alpha. And as the material is coming towards you in the rotating magnetosphere, it's going to be blue shifted. As material is moving away from you, it's going to be red shifted. And if we could fly to this star and look at it with H alpha glasses, what we would see would be something like this. We would see a blue shifted half hemisphere coming towards us and a red shifted hemisphere going away from us. Now, if you look carefully, you'll notice that most of the plasma tends to be concentrated in these two knots. that's actually the intersection between the magnetic equator and the rotational equator. That turns out to be the absolute minimum of the potential anywhere around the magnetosphere. And so most plasma tends to accumulate at this intersection. So not only do we have a magnetosphere, we tend to have two very distinct clouds that are fixed in geometry by the physical geometry of the magnetic field. Now, the neat thing about this is that, of course, we can't fly. We don't have the advantage of being able to go and look at this the way we can the sun. We don't have the ability to resolve this magnetosphere. But we do have, this is the star Sigma Ori. This is where it sits in the sky. There's the Orion's belt. You go just south of that, and it's down here. There's a Sigma Ori complex, and this is the E component of that small cluster. But now the point is that you can actually, let's see, I'm going to see if I can do that. You can actually now generate synthetic diagnostics of things that we can observe, even though it's a star. One of the things we can observe is the photometry. Every time one of these clouds goes in front of the surface of the star, it's going to absorb some of the stellar light from the surface of the star. And so that the light dips. But then these H-alpha is going to be varying in a very distinctive way. You can see how the H-alpha line profile is just varying in a very, very complex way. Here's the spectral polarimetry that is telling us what the magnetic field geometry is. So these three diagnostics are very strongly constraining your model. So let's just look what happens if we now take the fact that we know from the spectral polarimetry that there's a magnetic field tilted by 55 degrees. We make one of these magnetospheres, and then let's just, to characterize this H-alpha, let's characterize it by what's called a dynamic spectrum. Dynamic spectra mean that you just take the brightness at any given phase of the rotation and you plot it as a color contour as a function of Doppler shift either to the blue or to the red of line center. And you get a very characteristic pattern. In other words, this pattern back here, this characteristic variation back here, is now just being rendered as a simple diagram. Let's see. I'll go away in a second. This is now the prediction of this model, a dynamic spectrum with a very complicated variation. Okay? And now this is what you observe with H-alpha observations. And you can see that there's very good agreement. There's almost no doubt that this star has a centrifugally rotating magnetosphere. Even though we can't look at it the way we can the details of the sun, we know as well as anything we know in astronomy that this star has a magnetosphere. So that's a great triumph. And very rarely in astrophysics do you get to have such great agreement between a simple model and theory and observations. And you have to savor it while you can. So let's just start asking ourselves, okay, this is now just showing a simple double. There's the sort of double wave of these clouds going around. Here's the H-alpha superimposed, this variation that you observe. There's sigma Ori in the diagram. There's the... Here, these are the parameters of sigma Ori. It's rotating at 1.2 days, has a 9 kilogauss dipole magnetic field. Those are its parameters for the Kepler radius and the Alfvén radius. And this is basically what the magnetic field looks like in this paper that was done by my postdoc, Rich Townsend. Mary Exala was my graduate student, who's now in Czech Republic. Now that, unfortunately, it's not all the stars. The star here has a very complex magnetic field, and its magnetosphere is very, its dynamic magnetosphere is much more complicated. And yet, even though the magnetic field, in this case, has a quadrupole and octupole moments, you can still use this simple model to define where the lines are. And if you have good enough observations, you can define where the magnetosphere should be. And you can actually make a dynamic magnetosphere, even though it's not, it's a very complicated thing. Now, of course, it's much more difficult to get this to agree quantitatively with the observations because they're so much more complex. But generally speaking, it's inconsistent. It's consistent with the fact that the magnetic field we know from this star from spectral polarimetry to be very complicated. And therefore, the magnetosphere is very complicated. And there you see the dynamic magnetosphere is much more complex. Now here's a star. Now, both of these previous stars, they were rotating pretty fast. 1.5 days, the other one was 1.2 days. So the Kepler radius is only about 1.6, 1.7 stellar radii. Here's a star that's rotating at 540 days. 540 days. It takes a year and a half for the star to rotate once. That makes even the sun seem like a rapid rotator. This can't possibly have a centrifugally supported magnetosphere. The Kepler radius is way, way out there now. And so what happens? What does the H alpha look like? Well, nonetheless, it has a very, very distinct modulation in H alpha, right, as a function of orbital phase, rotational phase. But it doesn't have this S wave. It either just grows and gets bigger and smaller. Well, it turns out that if you just take now this dynamically suspended magnetosphere, if you just take simulations of this dynamically suspended magnetosphere, average over time of all the balls being juggled up in the air, and use that to synthesize a synthetic H alpha, that's what you get. And if you just broaden that a little bit with what's so-called turbulent broadening, you can match the observations really quite well. And we're actually working on refining this model. But it's quite remarkable that even the dynamical magnetospheres, and this star is an O star, so it has a much stronger mass loss rate. So even though the material doesn't stay suspended very long, it still can emit quite a bit of H alpha. So we basically have these dynamical magnetospheres, and we have these centrifugal magnetospheres. And we're in the process of sorting through them all, explaining all this complex spectral variation that we see. All right, so let's go back to this photometry result. This is now photometry that's taken. This photometry was taken, I'm not sure exactly, published in 2005 with this colleague Detlef Grote. But here is basically the predictions of the rigidly rotating magnetosphere model. And there's the data. You can see there's some problems with this is probably photospheric signatures due to the abundance anomalies. But basically, the dips are being very well produced. And this kind of photometry has been taken back. And then this is the magnetic field. This longitudinal magnetic field also matches quite nicely the observations. And so the model also fits the photometry and the spectrophotometry quite well. Now, the key point here is that photometry is easy. And in principle, when this star was first detected to have a magnetic field, you would think people would just monitor it. So sure enough, in the 1970s, people took photometry of it, and they saw these little dips. But in the time from the 1970s until about 2000, when my students started observing it regularly, it never was really observed, even in just photometry. The problem with that, but now we have observed it, and we find that these dips are very stable. They're still there after 30 years. And now what we can do when we have such good observations is we can actually go back and put this on what's called an observed minus computed diagram. That is, we measure the timing of that eclipse. And since you're doing it over 30 years, 1.2-day rotation period, you can get the rotation period to this star to very high accuracy, 7 decimal places. Now, if we knew the rotation period of 7 decimal places, it would fit. Say we were off. Say it was a constant rotation, but we were off. We would just find a drift in the observed minus computed diagram along this dashed line. And that would be the result. The star actually had a different rotation period. We have to adjust our guessed rotation period. But we find that, to the contrary, even though the star wasn't observed in all this time in between, we have been observing it for the last 5 or 6 years. And now we find to a 5 or 6 sigma that is inconsistent with a straight line. It has to be fit by a parabola. And when you have a parabola in an observed minus computed diagram, it means that you have a change in the rotation period. There's a change in the rotation period. In this case, the change in the rotation period is such that the star is spinning down. As an E-fold spin down time, its period is increasing on a time scale of 1.34 million years. So we have directly observed spin down of this star. we know that this star is not only has a magnetic field, but it's actually slowing its rotation. Now, why is it slowing its rotation? Well, it's clearly because, it's very likely because when stars rotate with magnetic fields, the magnetic field provides a moment arm, and you lose a lot more angular momentum than you would if you didn't have the magnetic field. And there's this simple formula that goes back to a paper in the 1970s by Weber and Davis that says the angular momentum loss rate is just the mass loss rate times the rotation frequency times the Alfvén radius squared. Now, when Weber and Davis first did this, they used a split monopole to treat their Alfvén radius. And in that case, the Alfvén radius only goes like 1 over the square root power of the confinement parameter. But for a dipole, it goes like the 4th root. And so for the dipole, there's quite a bit of difference in the Alfvén radius than what you would get from a monopole. The point is that now we can use the dipole variant of this formula to predict a spin down time. And it turns out to follow this simple formula. And in a paper in 2007, 2007, 2 years before the observation of the spin down, we have a table predicting the spin down times of various stars. And you can see sigma or E was predicted to have a spin down time of 1.4 million years. And then 2 years later, we observed it, and it has a spin down time of 1.34 million years. So that's very good agreement, almost better than you would expect. Moreover, this star that's very slowly rotating has a very short spin down time. If it's only a few million years old, if it's like, say, 3 million years old, then it's had many, many E-folds to spin down. It's spun down by E to the 6th or 7th. And that's enough to take a star from 1 day rotation period to 538-day rotation period. This star almost certainly has been spun down due to the fact that it has a rotating magnetosphere.
Questions, comments?
Thank you for the talk. Is this working? For the majority of the stars, the massive stars do not have such strong magnetic fields. Are there disks? Have they disks around the disks of the stars that do have strong magnetic fields?
Very, very steady. Doesn't show the kind of rotational operation. And all of that is pointing to the idea that those stars, which really making the acceleration, has actually been ejected into orbit from the star somehow. And it's in capillary orbit, which is sometimes called a decretion orbit. You know, we have two stars, and you have mass flowing from one star, the other constellation tends to form an accretion. Very rapidly rotated, very close to critical. That W parameter is very close to 1. And any small ejection of diameter star can actually up there. And then that material up there goes into a temporary disk. Now, there's a big debate that's going on for about 10 years about whether magnetic fields play a role in that. And it's possible that there's a small field magnetic field that causes the projection off. It's like a solar flare. But when we look at these disks in general, we often see that over a time scale of maybe 7 years, the H alpha slowly varies from the violet component to the stronger in the red. This is reversible. But this takes years. In the case where we have multi-body rotation, that happens when we do the rotation for a couple of days. This is happening over a very long time. What do you think about that? What that's telling you is that there's some part of the disk which is coming towards you that's brighter over many, many years. And then it slowly goes around. That must mean that the material in the orbit is going around every couple of days. So it's kind of like it can't be an actual plasma that's moving around physically. It must be a wave. And so the best model for that is that this is one density. And it has this link to precession. The fact is that the star is great potentially the vertical level or the line. And therefore the material, if the disk is made up of material orbit, this then orbit persists for kind of years. Now precession is a slow process precisely because the only two forces are gravity and inertia. If you only have precession with an other force, it's tiny. So what that's telling you is that in a global sense, magnetic field cannot be according to the dynamics of the main star. Because the object has this long-term bipolar radiation. So the answer is probably is that capillary with the base are at capillary units that are not primarily associated with magnetic field. Although it could be localized magnetic field on the surface that play a role in chances of material to work. So only either these stars are capillary units and not magnetic. And indeed, the minds who go out and observe stars, we've observed many, many stars that are not. And of the 50 these stars that have been monitored with spectral photometry, 0 turned out to have wax and so there seems to be a contrary for these stars and anti-correlation with the magnetic field and their P. But the P colors are different. P takes cooler out at the well longer conservative intersection with exclusion of elements. And so, okay.
Thank you.
question. As far as I know, one of the major problems concerning massive stars is the discrepancy between observed and predicted radii for Wolf-Rayet. The difference in the measurements and the theoretical prediction concerning the radius of Wolf-Rayet star. This combination of magnetic field, maybe at lower extent, and winds, can provide some explanation of this? Or?
What? Okay. Because the magnetic fields are so strong in these stars, you expect, as is happening in the sun, that the physical properties of the photosphere are going to be correlated with the presence of a magnetic field on the surface. So you expect that this also modulates the light curves and the emission in HR, all these kind of things. Okay, so the question is whether this is important and whether you have taken this into account when you are making the models.